learn the construction rules with the help of which we can construct an approximate root locus with ease. Now, the first rule number one, actually doesn't help us in constructing the root locus. But after construction, when you develop the complete root locus, am I audible?
Yes, ma'am.
And can you see the material?
Yes,
Yes,
ma'am.
ma'am.
Okay. So after constructing the complete root locus, you must check this particular rule, right? If the rule is not satisfied, that means the root locus that you have drawn, that you have sketched, is not correct. So what is the first rule? Rule number one: the root locus is symmetrical about the real axis, that means sigma axis. So after constructing the complete root locus, you must look at your sketch and should check whether the root locus is symmetrical about the real axis or not. And as I said, if it's not the case, then something is wrong. So, what is the basis for this rule? We know that the roots of the characteristic equation could be either real or could be complex conjugate pair, right? So that's why the root locus will always be, or any combination of these two. So the root locus will always be symmetrical about the real axis, right? Now let's come to the second rule. Already we have discussed this particular experiment. Let me get back to that experiment where we discussed a second order system. Yes, this one. And we discussed that the open loop pole locations on the S plane are at S equal to 0 and S equal to minus A. Also, we have derived the fact that when the value of the variable parameter or variable gain k is equal to 0, we found that the root branches were originating from these two open loop poles. Can you recall? This is the first root branch, or this is the second root branch. This one is one root branch, this is the other root branch. Okay, and both the root branches are originating from two open loop poles when k is equal to 0. Can you recall this fact? Yes or no?
Yes, ma'am.
Okay. So what is this rule all about? So when as k increases from 0 to infinity, we are varying the gain k from 0 to infinity, and when the value of gain k will be 0 for an nth order system, n number of root branches will originate from n number of open loop poles, right? And as k tends to infinity, now out of those n number of root branches, m number of root branches will terminate on m number of open loop zeros. That means we are considering a generic nth order system. So an nth order system will have n number of open loop poles, that is clear, and we are assuming that the open loop number of open loop zeros is equal to m, right? Now we are increasing the value of gain k from 0 to infinity. Now when the value of gain k will be 0, n number of root branches will originate from n number of open loop poles, and as k will tend towards infinity, out of those n number of root branches, m number of root branches will terminate. As k tends to infinity, m number of root branches will terminate on m number of open loop zeros. Clear?
Clear, ma'am.
Okay. Now, what about those n minus m number of root branches? We know since the system is an nth order system, so number of root branches will be n. So
Infinity. It will become
number
zero.
of root branches will be n, right? So
Yes,
what
ma'am.
will happen to the rest of the n minus m number of root branches? So as k tends to infinity, those n minus, if m is less than m, sorry, m is less than n, then n minus m number of root branches will tend towards infinity as k tends to infinity. So the rule states that as k increases from 0 to infinity, each branch of the root locus originates from an open loop pole with k is equal to 0 and terminates either on an open loop 0 or on infinity as k tends to infinity, right? So the number of branches terminating on infinity equals number of open loop poles minus number of open loop zeros. Now what is the basis of this particular rule? It's a simple rule. We can very easily derive the rule. Now remember the characteristic equation QS of an nth order system can be represented as 1 plus k into product of s plus zi's divided by product of s plus pj's. Can you relate the equation?
Yes, ma'am.
So that means we can write the equation. Okay. So this is our equation. This is our equation. So we can write this equation as a product of s plus bj's, where j is varying from 1 to n, plus k into product of I varying from 1 to m, s plus zi is equal to 0, right? So the characteristic equation can also be written in this form, right? So in this equation, you see, if we put the value of gain k to be equal to 0, then this all these terms will be 0. Okay. So the characteristic equation when the value of gain k is 0 will have n number of roots located at minus pj's. You get my point? You get my
Yes,
point?
ma'am.
Ma'am.
Yes, ma'am.
So minus pj's, what are these minus pj's? The minus pj's are the locations of the open loop poles of the system on the S plane. So we see that when the value of gain k is equal to 0, n number of root branches will originate from n number of open loop poles. Now again this equation, we can divide this equation by k. So if we do so, then the equation will become 1 by k product s plus pj plus product s plus zi, and that is equal to 0, right? So when k will tend towards infinity, now all these terms will now become zeros, right? And now we are getting m number of roots of the characteristic equation, and we find that those m number of roots are located at minus zi's. And what are these minus zi's? Minus zi's are the locations of the open loop zeros of the system. Clear?
Clear, ma'am.
and hence the rule. Okay. Now the third part, that is, if m is less than, in commonly occurring cases, we find that number of zeros are much less than number of poles, or we can say that number of zeros are generally less than or at best can be equal to the number of poles. I'm talking about open loop poles. Okay. So that means n minus m. What will happen to this n minus m number of root branches? Already we have seen that this n minus m number of root branches will terminate, tend towards infinity as k tends towards infinity. So how can we derive this fact? Now this equation, just think of the magnitude criterion. This is the magnitude criterion. Can you recall this? This is the magnitude criterion. Can you
Yes, ma'am.
recall
Yes,
this?
ma'am.
Okay. Now you can do it. Just do it. Otherwise you'll get confused. Now from the numerator, from just consider the left hand side of this equation. So from the numerator we can take common s to the power m, that particular term. So here we can take out s to the power m, that particular term, out of this product sign. So the terms within the bracket will now become 1 plus zi by s.
Yes, ma'am.
Have you done this? The same thing we are doing for the denominator polynomial. Now in this case we are taking out s to the power n terms out of this product sign. So within this bracket we'll get the terms like 1 plus pj by s.
Yes, ma'am.
And obviously the right hand side is 1 by k, right? So in the denominator, since n is greater than m, so in the denominator we'll be left with a term which is s to the power n minus m.
Yes, ma'am.
Okay. Now, so when, if we assume that a point on the root locus is lying at infinity, then that particular point, that onlooker's point, can be represented by this expression: s is equal to infinity e to the power j phi. S is a complex number. It will have a magnitude as well as a phase angle. So this is the phase angle part, and since the point is located at infinity, hence the magnitude will be infinity. So s will be infinity e to the power j phi. Here.
Yes, ma'am. Clear.
So in the left hand side, if we put the magnitude of s to be infinity, the left hand side will now become 0,
Yes, ma'am.
right? And the equation will be satisfied only when k is infinity or k tend towards infinity, isn't it? In that case the right hand side will
Yes, ma'am.
also be 0. Okay, so that's why the third part of the rule, that is, as k tends to infinity, the rest n minus m number of root branches will tend towards infinity. Clear?
Clear, ma'am.
Okay, I'll come to this rule, rule number 3, after discussing. In this particular book the rules are given in this particular order, but generally I prefer to discuss rule number 4, as it is directly related to the second rule that we have discussed. So rule number 4 and 5 we'll discuss first, and after that we'll focus on rule number 3. There is no specific order. In this book, they have presented the rules in this particular order. So one by one, you will have to apply the rules. So what is rule number 4? The n minus n number of branches which are tending towards infinity as k tends to infinity will do so along straight line asymptotes. Along straight line asymptotes, the angles of the asymptotes are given by phi a. Generally, we use the symbol phi to represent, and A stands for asymptotes. So, asymptotic angles are given by 2q plus 1 into 180 degree divided by n minus a, divided by n minus m, and q will vary. You see, n minus m number of root branches will tend towards infinity, right? So for that means we will get n minus m number of straight line asymptotes. Okay, so that's why in this equation q will vary from 0 to 1 to up to n minus m minus 1. Clear? Now, this
Clear,
rule
ma'am.
can also be uh, derived very easily, but since I can't do board work, that's why I don't know whether you'll be able to appreciate the um, essence of the rule or not. Just think about a point which is an onlooker's point, but located at infinity. Right? We are talking about the root branches which are tending towards infinity as k tends towards infinity. So, if we consider a point, onlooker's point, which is located at infinity, then at that particular point, on the root locus, all the open loop poles and zeros, will contribute almost same angle, same phase angle. You get my point? Suppose on the real axis, suppose these two are the two open loop poles, and I'm considering this open loop poles to be very close to each other because I'm considering a point which is suppose located at infinity. So if I join the point to the poles on the real axis, right? So, and if these lengths are pretty large, then we can argue that the angles, contributed by the poles at this point, which is lying at infinity, will be
Be
almost
same.
same, right? So, if we consider the angle to be phi, angles contributed by all the open loop poles and zeros at a point which is an onlooker's point and lying at infinity, almost infinity, then the angle contribution of all the poles and the zeros will be minus n minus m into phi. Phi is the angle contributed by each pole, open loop pole and open loop zero, right? So angle of GSHs will have to satisfy angle criteria. We'll have to check angle criteria at that particular point. So angle GSHs will be equal to minus n minus m into phi, right? And since the point is one onlooker's point, so at that point the angle criterion will be satisfied. Hence, minus n minus m into phi will be equal to plus minus 2q plus 1 into 180 degree. This is our angle criterion, right? And we are joining the point, or rather, we are joining the point and the open loop poles and zeros with the help of straight lines. So the those straight lines could be considered as straight line asymptotes, and hence the asymptotic angles phi from this equation phi can be derived as plus minus 180 degree to q plus 1 whole divided by n minus m, and that is our rule. Have you understood this?
Okay, ma'am.
So these are the asymptotic angles, and just remember that q will vary from 0 to n minus m minus 1, and that's why we'll get n minus m number of asymptotic angles. So since we have derived the angles, asymptotic angles, then we can draw the straight lines, can we? Can we draw the straight lines or asymptotes?
Yes, ma'am.
Yes, only we know the angles, slope angles. Is it possible to draw a straight line if only the angle or the slope is known?
No, ma'am. From that point, we need that point from which it will deviate, right?
It's not really. We need another point, one point, right?
Yes, ma'am.
So, hence the next rule, that is, the asymptotes will cross the real axis. All the asymptotes will pass through a single point which is located on the real axis, and that point is called the centroid. Right? So what is written over here? The asymptotes cross the real axis at a point known as centroid. Okay, so if we can determine the centroid, then we'll be able to draw all the straight line asymptotes because we know the angles, and we know that all the straight lines or straight line asymptotes will pass through this point on the real axis, which is centroid. So how to find out the centroid? The formula is this one. So centroid, just ignore this minus sign. Centroid is denoted by the symbol sigma e. This convention, sigma e. Sigma e, the centroid, is equal to summation of real parts of the poles minus summation of real parts of zeros. That means for complex poles, we are not considering the imaginary part. For complex zeros, also we are not considering the complex part. So summation of real parts of the poles minus summation of real parts of zeros divided by number of poles minus number of zeros. So divided by n minus a. Clear? So with the help of this formula, we can find out the location of the centroid on the real axis, and hence we can find draw the asymptotic straight lines. Uh, I'm not showing the derivation of this for this particular rule. Now, just ignore this minus sign. Why? Because uh, this is a convention in some books. You'll find that they have represented sigma a as minus sigma a, but the problem is if after calculation the value comes out to be minus 2, then it might happen that you'll get confused, and finally you will write down that sigma a is equal to only 2. You get my point? Since it's written over here minus sigma a, and if the value comes out to be minus 2, then you might get confused. Actually, centroid is denoted by minus sigma a. Just ignore minus. So if the value comes out to be minus 2, then sigma a, the centroid, will be located on the real axis at minus 2. And if the value comes out to be plus 2, then the centroid will be located on the sigma axis at plus 2. Have you understood what I'm saying?
Yes, ma'am.
Okay. Now, also remember one thing, that centroid is not an onlookers point. It's not necessarily an onlookers point, right? Centroid is a point through which all the asymptotes will pass, and it's basically located on the real axis. but it's not an on locus point. So at the centroid, the angle criterion, it's not necessary that the angle criterion has to be satisfied. It might so happen that the centroid uh, that you compute will lie on the on locus, but it may lie on the on locus, it may not lie on the root locus, but it's not, as it's not an on locus point. So let's come to now. Let's come to the so this rule. Now a point on the real axis will lie on the root locus if the number of open loop poles plus open loop zeros lying to the right of the point is odd. I repeat, with the help of this particular rule, we are trying to find out which part of the real axis will be an on locus segment. Am I clear? So this rule will help us in finding the segments of the real axis, the segments which are basically on locus segments. Here, so the rule states that a point on the real axis will be an on locus point or will lie on the root locus if the number of open loop poles plus open loop zeros lying to the right of that particular point is odd. Then the point will lie on the root locus.
Okay, ma'am.
So let's look at this diagram. So these are the locations of the open loop poles and zeros. So the starting point of constructing a root locus or sketching a root locus is to, first of all, is to place the open loop poles and zeros on the S plane. And also please note that since you're working on the S plane, you'll have to level this to axis. This is the real axis, sigma axis. This is the geometric axis. Okay, fine. So these are the open loop poles P1, P2, P3. These three are the open loop poles, and zeros are here. Z1 is one zero and Z2 is the second zero, as can be found from this particular figure, right? Now, here this point has been taken as the trial point. So we are trying to find out whether this point will be lying on the root locus or not. Okay,
Yes, ma'am.
so for that, now we see that these are the open loop poles and zeros. These two open loop poles and this particular open loop zero, real open loop poles and real open loop zero are lying to the right of this point, isn't it?
Yes, ma'am.
And this two real open loop pole and zero, these two are lying to
Yes,
the
ma'am.
left of this particular point, trial point, right? Now,
Yes, ma'am.
as per the rule, if we add the numbers of real open loop poles plus real open loop zeros, we find that 1 plus 1 plus 1. So three open loop poles plus zeros are lying to the right of this trial point, and 3 is an odd number, and hence this point, as per the rule, this point will be one on locus point. On locus point. Right? Now, what is the rationale behind this? Again, you see, if we this is the trial point, so let's construct this phasor S0 plus P2, S0 plus Z1, S0 plus P1. Similarly, S0 plus Z1, S0 plus uh, I guess this is P3, S0 plus P3. These are the real open loop poles and zeros. Along with this real open loop poles and zeros, the system has two complex conjugate pole pair, which we have not considered. Okay, so why? Let's see. So these two are the two open loop complex conjugate pole pair, right? Now, after constructing all these phases, since this is the trial point, we see that at this trial point, the open loop poles and zeros which are lying to the right of this trial point are contributing an angle which is equal to 180 degrees. So this particular pole is contributing an angle at this trial point which is equal to 180 degree. Again, this particular zero is contributing an angle at this trial point which is equal to 180 degree. Am I clear?
Clear, ma'am.
And the real open loop poles and zeros lying to the left of this trial point, the angle contribution, look at this phasor, the angle contribution is zero.
Zero.
Right. The angle contribution will be zero for. And similarly, if we consider the complex conjugate open loop pole pair or zero, pair of zeros, then this angle plus this angle, that means 360
Zero.
degree, exactly zero. That means only the open loop pole, real open loop poles and zeros lying to the right of this point are contributing an angle of 180 degree each, right? So if we assume that m number of open loop zeros, real open loop zeros, lying to the right of this pole, the right of this trial point, and inner be the number of real open loop poles lying to the right of the trial point, then MR minus NR into 180 degree will be the angle GSHS,
Yes, ma'am.
right? Now, for this particular trial point to be one onlooker's point, this MR minus NR into 180 degree should be equal to plus minus 2Q plus 1 into 180 degree, which is our angle criterion. So
Yes, ma'am.
from this, you see, we can conclude that MR minus NR should be odd, isn't it?
Yes, ma'am. Yes, ma'am.
So if MR minus NR is odd, then MR plus NR will be odd.
Yes, ma'am.
So MR plus NR will also be odd. So again, let's get back to the rule. Let's see the statement. A point on the real axis lies on the locus if the number of open loop poles plus zeros on the real axis. That means real open loop poles plus real open loop zeros lying to the right of the point is odd. So once we understand this particular rule, then some interesting observations can also be found. Now, number one, see, in this case, we find that this point is one onlocus point. That means this trial point, yes, this trial point will lie on the root locus. Okay. Now, first thing which we can observe that this real open loop poles and zeros actually divide the real axis, divide the real axis into segments. So this is one segment, this is another segment, this is another segment, and this particular segment, this is another segment, and this segment has infinite length. Have you understood this? So what is the first observation? The observation is real open loop poles and zeros are dividing the real axis into segments. Clear?
Clear, ma'am.
So if a point is one onlookers point, then all the points, if I shift this point towards right or towards left, all the points on this particular segment will be onlookers point. Because if I shift the point at this position, then again you see the number of real open loop poles plus real open loop zero is odd. The number is odd. So that's why this point will also be an onlookers point. Again, if I shift the
Yes, ma'am.
point at this point towards left, the point will be one onlookers point. How long? Unless we cross one real open loop pole or open loop zeros either in this direction or in this direction. So once we cross this open loop pole, while shifting this point, the entire segment is one onlooker segment. So if we start shifting this trial point, and in the process, if we cross this open loop
It will be
pole,
two.
it will be two.
Yes,
Hence,
events.
hence this particular segment. Now see, this entire segment will be one not onlooker segment. None of the point on this segment
Yes, ma'am.
will lie on the root locus. Again, if we cross one open
Between
loop,
Z1 and the
yes,
P1. Yes, ma'am.
then this segment, in this case, you see the segment will be onlooker segment, right? So
Yes, ma'am.
if we mark the segments, onlooker segments and not onlooker segments, with a different color, right, we'll find that the
It will be
real axis,
alternative.
yes, alternating the onlookers and non onlooker segments will alternate.
Yes, ma'am.
So will alternate. This one is onlookers, not onlookers. This entire segment is onlooker segment, and this infinite length segment is not onlooker segment. So let's consider a system having this open loop transfer function. The transfer function is k into s plus 1 into s plus 2 divided by s into s plus 3 into s plus 4. So from this open loop transfer function, it's clear that the number of open loop poles is equal to 3. One located at s equal to 0, the second one at s equal to minus 3, the third one is at s equal to minus 4. A transfer function to लिखे रखो.
Okay, ma'am. Done.
And two open loop zeros, one at s equal to minus 1 and the other one is at s equal to minus 2, right? So from this it's clear that n minus m is equal to 1. So if we want to sketch the root locus, the rules that we have studied so far, with the help of those rules we can draw the complete sketch, complete root locus plot of the system. So what are the locations of the open loop poles? One at s equal to 0, the
0
other
minus
one
3
minus
minus 4.
3. So with the cross, with the help of a cross, you should uh, denote the presence of an open loop zero is, oh sorry, open loop pole, and with small circle open loop zeros. Okay, so these are the three open loop poles. So we know that three open loop root branches will originate from this three open loop poles when the value of gain k is equal to 0. So this is one root branch, this is another root branch, this is another root branch. Now let's apply rule number 3, the rule that we have just done. Okay. So we find that this particular segment is one onlooker segment. Take any point on this segment and count the numbers of open loop poles plus zeros lying to the real
One.
open loop poles. Yes, that is one. So the entire segment will be one onlooker segment. Hence, again, you can apply the rule, but it's pretty easy. This segment will be one not onlooker segment, and again this segment will be one onlooker segment, and this infinite length segment will be one onlooker segment. Is that clear?
Yeah, ma'am.
Okay. Now, one root branch will originate from this open loop pole when k is equal to 0. And since this is one onlooker segment, and this is not one onlooker segment, right? This is not the onlooker segment. So, the root branch will originate from this particular open loop pole and will
Yes, ma'am.
terminate onto this open loop 0, because there is no other path, right? So the root branch
Yes,
will
ma'am.
originate from this open loop pole, and the root branch will move along this direction in the direction of arrow. And in root locus sketch, again, arrow directions are masked. So this root branch will move like this, and ultimately it will terminate onto this open loop 0. Similarly, the second one will originate from this open loop pole. Now this segment is one not onlooker segment. Hence the root branch cannot move along this direction, right? So the root
Yes,
branch
ma'am.
will have to move in this particular direction, as this one is one onlooker segment, and again the root branch will originate from this open loop pole and will terminate on this open loop 0. Here, how many straight line
Yes, ma'am.
asymptotes will be present in this case? N minus m is equal to 1.
Yes, ma'am.
So what will be the asymptotic angle? 180 degree to q plus 1 divided by n minus m. Now n minus m is equal to 1 and q
One.
value is 0, right? So the angle, one single asymptote, straight line asymptote,
180 minus 4 to
angle
infinity.
exactly minus 4 to infinity. So simple. With these three rules only, we can sketch the complete root locus plot of the system. Right? And I'm not discussing uh, this plot in detail because we'll solve other problems as well. So from this root locus plot, you see no root branch is moving in the right half of this plane, isn't it? All the three root branches
Yes,
are
ma'am.
confined, completely confined in the left half of the S plane. That means the for any
Yes,
value
ma'am.
of gain k from 0 to infinity, the system
It
will
will be
remain
stable.
stable, right? So again, let's consider a second example. So this part is the open loop transfer function GSHS k into s plus 1 plus s plus 2. If the characteristic equation is given, then from the characteristic equation, we'll have to find out the open loop transfer function. So this is the open loop transfer function, and these are the root locations. A is equal to 0, A is equal to minus 1, A is equal to minus 2. So now the as number of open loop 0, 0, and number of open loop poles 3. So n minus m will be equal to
3.
3. So we'll get three asymptotes, straight line asymptotes, and the asymptotic angles will be given by this formula 2q plus 1, 180 degree, divided by n minus m, which is 3, and q will vary in this case from 0, or the values of q will be 0, 1, and 2. So the asymptotic angles will be 60 degree, 180 degree, and 300 degree. So whenever n minus m value will be equal to 3, you will get three asymptotes having angles 60, 180 degree, and 300 degree. Similarly, if the angles n minus m is equal to 4, if the difference is 4, then the asymptotic angles with the first asymptotic angle will be 45 degree, and the other three asymptotic angles will be odd multiple of 45 degree. Got it?
Yes, ma'am.
Already we have seen that if n minus m is equal to 1, there will be single asymptote having asymptotic angle which is equal to 180 degree, and if n minus m is equal to 2, then we'll get two asymptotes having angles plus minus 90 degree. That's simple. So asymptotic angles we have calculated, we have computed. Now we'll have to find out the centroid. So sigma A, real parts of poles minus real parts of zeros. This is n minus m, and real parts of the poles. Poles are located at 0,
0 minus 1 minus 2.
0, minus 1, minus 2. So minus 3, summation of real parts of the poles. So that is minus 3 divided by 3. So the location of the centroid sigma A will be on the negative real axis at minus 1. Now we can draw the root locus, we can sketch the root locus. You see three root branches, one originating from the open loop pole, which is at s equal to 0. The second one is originating at from an open loop pole, uh, which is located at s equal to minus 1. And third one is originating from an open loop pole which is located at minus 2, right? So this is one on locus segment, this is the on locus segment, clear? So one root branch will originate from this and will move in this particular direction. The second root branch can't move in this direction as this segment is not an on locus segment. So this root branch will have to move in this particular direction. So two root branches are approaching each other along the real axis, and at a certain point these two root branches will meet. And as we have seen for the second order case, if we now increase the value of gain k beyond this value, these two real root branches, if the root branches are along real axis, then we call those root branches as real root branches. So these two real root branches will break away from this particular point, and they will form two complex conjugate root branches. Now you see, this is our centroid minus 1. This is the centroid, and we have drawn the asymptotes. This is the asymptotic line, straight line having an angle 60 degree. This is the asymptotic straight line having an angle which is 180 degree, and this is the third asymptotic straight line having an angle 300 degree. You see the asymptotes are symmetrical about the real axis, right? So one root branch will as k increases, one root branch will tend towards infinity along this straight line asymptotes. Can you follow?
Yes, ma'am.
Similarly, this root branch will again tend towards infinity, no open loop zeros. Hence, all the three root branches will tend towards infinity as k tends towards infinity. So, this root branch will tend towards infinity along this asymptotes. And the third root branch, this is an on locus segment having infinite length. So, the third root branch will originate from this open loop. pole and will tend towards infinity along the negative real axis, and the asymptotic angle is 180 degree, right? Only the thing that we don't know yet, that is the point at which, the point on the real axis at which these two root branches are meeting with each other. Okay, so we'll see that. Otherwise, for the time being, let's assume that we know that this particular point, then we can draw the root locus. And after completing the root locus, you see, we find that the root locus is absolutely symmetrical about the real axis, isn't it?
Yes, ma'am.
So given a value of gain k, we can find the roots. One root, second root, and the third root will be on this branch. One root will be on this branch, the other root will be on this branch, or it might so happen that one root will be on this branch, the second root will be on this branch, and the third root will be on this branch. And just come, if we compare this root locus with the previous one, you see, for a certain value of gain k, this root branch as well as this root branch, these two root branches are intersecting the imaginary axis, isn't it? These are the points of intersection, which are
Yes, ma'am.
again symmetrically located. And we have already studied stability criterion. So we observe that this is the value of gain k. At this point, the value of gain k will be the limiting value. Why? Because if we increase the value of gain k beyond that particular value, two root branches will move in the right half of the spleen.
Yes, ma'am.
Got,
Yes, ma'am.
got it? So that means
Yes, ma'am.
if the value of gain k exceeds this limiting value, that means two will get two roots of the characteristic equation in the right half of the spleen, and the third root will always be in the left half of the spleen, right? But since two
Yes, ma'am.
roots are lying in the will be lying in the right half of the spleen, hence the system will be unstable. Clear? So this point is of
Yes,
interest,
ma'am.
as well as this, the points of intersection of the root locus with the imaginary axis is of importance to us. Now this point where the root branches, two real root branches are meeting with each other, is called the breakaway point. Why? Because if we increase the value of gain k beyond the value of gain k at this point, then these two root branches will break away from each other and they will form two complex conjugate root branches. That's why this point is called the breakaway point. And also, just please note that this point, this point is common to this root branch as well as this root branch, isn't it? The point, we can say that this point is lying on this root branch as well as this point is also lying
Yes, ma'am.
on this root branch, right? A common point. So if the value of gain k is k1 at this point, then for that particular value of gain k, will get at this point will get repeated roots with multiplicity 2. Clear?
Yes, ma'am.
Clear?
Yes, ma'am.
Already we have seen that this is the breakaway point. At that time we didn't use the
Yes, ma'am.
term breakaway point, but this is the breakaway point.
Minus a by
where-
2 times
yes,
there.
yes,
Yes, ma'am.
where the two root branches are meeting, and we have derived that at this point, yes, repeated roots of the system are occurring, and since two root branches are meeting with each other, hence the order of multiplicity is 2. So we can generalize this concept and we can say that if a number of fruit branches approach each other and meet at a point, and after that, if they break away from that particular point, then at that breakaway point, repeated roots of the system will occur with an order of
Yes,
multiplicity
ma'am.
equal to n.
Yes, ma'am.
So the next rule, I don't know whether you can see this one or not. Okay, I guess this is rule number 6. Rule number 6, central was rule number 4 in their order. Rule number 6, how to find out that breakaway point. Because if we cannot find out the breakaway point, then we'll not be able to accurately sketch the root locus. So the breakaway point, and what is the definition of breakaway points? Points at which multiple roots of the characteristic equation occur. That means at breakaway points we'll get repeated roots of the characteristic equation. So the breakaway point of the root locus are the solutions of this equation dkds equal to 0. Right? So dkds will have to take the first derivative of this with respect to s, and we'll have to form this equation dkds equal to 0, right? And the solutions of this equation will be the breakaway points of the system. Now also note that not all the solutions of this equation will be the breakaway points. No. It might so happen that this is we'll get a fourth order system, and if we take the first derivative with respect to s, we'll get a third order polynomial, and if we equate that to 0, then we'll get an equation having an order which is equal to 3. So if we solve the equation, we'll get 3 roots, right? But not necessarily all the 3 roots will be the breakaway points for a given system. It may so happen that only one single root will be the breakaway points. So the roots, the roots of this equation which will satisfy the angle criterion. Remember, breakaway point is one on locus point. Why? Because at that point, multiple roots of the characteristic equation occur. So, at the breakaway point, the angle criterion has to be satisfied. So, only the roots of this equation which satisfy the angle criterion will be considered to be, or will be, the breakaway points for the system. Am I clear?
Clear, ma'am.
I'm not discussing the derivation. So let's try to solve for the breakaway point. Close for this. Anyway, what was the equation? Characteristic equation. One. I'm trying to recall. One plus. Please help me. One plus k by s into s plus one into s plus two. I guess now equal to 0. The last example. Please respond.
1 plus k into 1 by s into s plus 1 into s plus 2.
That means k by s into s plus 1 into s plus 2 is equal to minus 1.
Yes, ma'am.
That means k is equal to, you see, now look at this expression. K is equal to minus s into s plus 1 into s plus 2.
Yes, ma'am.
So from the given open loop transfer function, we'll have to write down k as functions of s like this. Okay? Then only we can take the first
Okay, ma'am.
derivative of this with respect to s. So if we multiply, or if we try to express this in polynomial form, then k will be equal to minus s cube plus 3s square plus 2s bracket closed, right? So now we can take the first derivative and can equate that to 0. So dk ds is equal to, now it will be a second order equation, 3s square plus 6s plus 2, simply a second order equation. So this is left as an assignment. I don't know whether the values are correct or not. So please solve this equation and try to find out whether the roots of these equations are correctly computed or not. So that we'll get two roots, one at, for the time being I'm assuming that these values are correct. So one at minus 0.423 and the third one is minus 1.577. Okay, so we are getting two roots of the characteristic equation. Just 1 second. We have tried to sketch the root locus for this particular system, and you see, just if we apply our common sense, then, or just if we look at the nature of the root branches, then it's clear that only this two root branch can meet at a certain point on the real axis, isn't it? Can you imagine any other breakaway
Yes, ma'am.
point? Can you imagine that there could be a second breakaway point?
No, ma'am.
No. Okay. So the solutions were, one was minus 0.423, and you see this point, if the solutions are real, then it's pretty simple for us. So you see this point is, yes,
It should be in
located,
between 0 and -1.
yes, and is located on the on locus segment, right? So automatically this point is satisfying, it's satisfying the angle criterion. And also intuitively we can say that yes, the breakaway point should lie between, as you said, -1 and 0. So this point does satisfy the angle criterion, and it's a point in between these two open loop poles. So at this particular point, these two branches will meet, and at this particular point, we'll get two roots of the characteristic equation. And if we increase the value of gain k beyond this value, then these two real root branches will break away and will form two complex conjugate root branches, right? And what about the second root of the equation dkds equal to 0? The second root was somewhere, so far I can recall, at minus
Minus
1.5.
1.5.
Minus 1.5. So minus 1.5 is somewhere over here. And you see that this is one not on locus segment. So at minus 1.5, the angle criterion will not be satisfied, isn't it?
Yes, ma'am.
So only this root of the equation dkds equal to 0 will be the breakaway point for this given system. Is this clear?
Yes, ma'am.
Okay. Now let's consider another case. Here you see we have two complex conjugate open loop pole pair, say located at -1 plus j plus minus j1. So these are the two complex conjugate open loop pole pair, and here we do have, no, sorry, at this point. I'm sorry. At this point, at s equal to minus 2, the system has got one open loop pole. Sorry, open loop 0
0.
at this point, right? So
Yes, ma'am.
we know that when k is equal to 0, two root branches will originate from this two open loop poles, which
Poles.
are complex conjugate in nature. So the root branches will be like this. That will find that how to find out the approximate nature of this root branches. So the root branches will be like this, or geometrically we can prove that this will be a part of a circle, right? And you see,
Yes, ma'am.
initially the root branches are complex conjugate in nature, okay? And
Yes, ma'am.
while we go on increasing the value of gain k, at this point, you see these two complex conjugate root branches
Yes,
are
ma'am.
meeting with each other. And if we increase the value of gain k beyond this value, then these two complex conjugate root branches will form, will now reduce to two real root branches. And
Yes.
it's clear that here n minus n
Just
is equal
opposite
to
to the
1.
previous one.
Yes. So one root branch will terminate onto this open loop 0, and the other root branch will tend towards infinity. This is one, this complete segment is one on-locus segment. So the other root branch will tend towards infinity as k tends to infinity, right? So generally, of to be more precise, this point is called a break-in point. Break-in point, though it's written over breakaway point, but often when two complex conjugate root branches meet on the real axis and after that they form two real root branches, that particular point is called break-in point. So this is one breaking point.
Okay, ma'am.
And there is another significance of this that can be explained on the real axis considering s to be sigma. You see, dk ds equal to 0. So dk ds equal to 0 means if we consider s to be sigma, that means dk ds on the real axis, the equation will be dk d sigma is equal to 0.
Yes, ma'am.
So on the real axis, at the breakaway point or at the break-in point, this equation suggests that the value of gain k will be extremized. That means either
Yes,
maximum
ma'am. Maximum or minimum.
or minimum. Right. So I have closed. So if we go by the definitions of breakaway and breaking point, this is one breakaway point. At this point, you see the value of gain k is increasing in this direction as well as in this direction, isn't it? And on the real axis,
Yes, ma'am.
just recall we have considered S to be sigma, indicating sigma. So on the real axis, at the breakaway point, the value of gain k is maximum. On the real axis, here the value of gain k is 0,
Yes, ma'am.
the value of gain k is increasing, the value of gain k is increasing, and at the breakaway point, the value of gain k is maximum. In contrast,
The second case, it will be minimum.
yes, let's see.
Right.
Here you see this is the breaking point. To be precise, this is the breaking point, right? So at this point, say the value of gain k is k1. Now, when the root branches move in this direction and or in this direction, the value of gain k increases and k increases towards infinity. So on the real axis, in case of breaking point, the value of gain k is minimum. Have you understood this?
Yes, ma'am.
Now, just like real roots, complex conjugate root pair also can have multiplicity greater than 1, right? We can have complex conjugate root pair with multiplicity greater than 1. Repeated complex
Yes,
conjugate
ma'am.
root pair, right? So, so that's why the breakaway points could be real, could be complex conjugate. If the breakaway point is a complex one, then it will have its conjugate part. Because root locus is symmetrical, and you see this root locus, this is also symmetrical about the real axis. Okay. Or combination of
Yes, ma'am.
this. So here is one example. I'm not discussing this example. Just go on applying the rules step by step, step by step. I'm just showing you the root locus. So four open loop holes. Just a moment. Four open loop holes, and number of open loop zero is 0, right? So four open loop, four branches will originate, and as I said, we see that the angles are for asymptotic angles are 45 degree, 135 degree, 10 to 25 degree, and the last one will be probably 315 degree. Am I right?
Yes, ma'am. Yes, ma'am.
And this is the centroid that you can calculate at cellular material. So we can go through this example. So four root branches will originate from this four open loop holes. So this is on the locus segment. So one root branch will move in this direction, the other one will move in this direction, right? And we'll find, later we'll learn another rule with the help of which we'll be able to find out the fact that the root branch which is originating from this complex pole will move in this direction. This angle will be minus 90 degrees. Will move in this direction, and the conjugate part will originate from this pole and will move in this direction, right? So these two root branches will meet on the real axis at this particular point, which is a real breakaway point. Which is a real breakaway point. Right? And after breaking away, these two real root branches will form complex conjugate root branches like this. One is this one, the other one is this one. So again, this root branch is coming from here, this root branch is going in this direction, so they will meet at this point, which is a complex breakaway point. Similarly, this root branch will
Yes,
move
ma'am.
in this direction, this root branch will move in this direction, they will meet at this particular point. They will meet at this particular point, and this is the third breakaway point, which is the conjugate pair of this breakaway point. So we are getting three breakaway points. One is a real breakaway point, and other two are two complex conjugate breakaway points. I guess yes.
Yes, ma'am.
Solves this equation, the third order equation. So I guess we'll be able to solve this. So you see, is equal to minus 2 and is equal to minus 2 plus minus j 1.45. Now, the problem with complex root of this equation is that if the root is a real root, very easily you can find out whether the angle criterion is been satisfied or not. That means by the fact that whether the point is lying on an onlooker segment or not. But if it's a complex root of this equation, not the root of the characteristic equation, like this. So at one particular point, at minus 2 plus j2.5, you apply angle criterion. That is mandatory. You get my point? Just intuitively, we can't draw
Yes, ma'am.
this, can't sketch this root locus. First of all, we'll have to establish, yes, 1 point minus 2 plus j 2.45, say, is one on locus point. Then only it will be the recurrent point. So apply angle criteria, construct a phasor, use trigonometry or from rectangular to polar with the help of this option. You find out the angles contributed by all the open poles and zeros at this particular point, and check whether the angle criterion is satisfied or not. If the angle criterion is satisfied at one point, that is at minus 2 plus 8.45, then automatically the angle criterion will be satisfied for the at the conjugate pair, that is at minus 2 minus j 145. So for both the points, you don't have to apply angle criterion. Just apply angle criterion for a single point, and automatically the other one, the conjugate point, will be the recurrent point without symmetry.
Okay, ma'am.
Okay. Look, two rules are left. So in the next class, we'll discuss these two rules, and then we'll start discussing Naismith's stability criteria. So what we have discussed in this class, do you have any doubt? Do you have any query? Any question?
No, ma'am.
নলেজ সেকশন থেকে কেউ আমাকে অন্য মেলে, মানে এই যে মেলটা থেকে আমি তোমাকে লিঙ্ক পাঠাই, এখানে অ্যাসাইনমেন্ট পাঠিয়েছো, ল্যাব অ্যাসাইনমেন্ট পাঠিয়ে তাহলে কনসিডার হবে না কিন্তু কিন্তু বেরিয়ে গেছে। দু তিনজন আমাকে এই মেলে পাঠাচ্ছে অ্যাসাইনমেন্ট, সেগুলো কিন্তু কনসিডার হবে না। So I'm ending this session.